Hey students, let's pick up where we left off. I was doing some examples. I did 3, and let's do the other 3. And so let's do number 36, 54, and 59 here. So number 36, and as you probably recall from the other video, I had printed these up, and so we did these first 4, and now let's do number 36 here. It says, in the Winter Olympics, an athlete rides her luge down the track while a bell rings above the wall of the chute, ringing continuously. When her sled passes the bell, she hears the frequency of the bell. Let me pause right there. So you might recall we've been doing some problems, or we had a part of the lecture. It's called the Doppler effect, where, let's see, if somebody is, say, traveling towards the source of sound, there would be this shift in frequency. Because if they were standing still, they might hear, the number of waves, let me just say 256, so 256 hertz. So 256 waves come to the person's ear every second. And if they move into it, it would be as if they were traveling a little bit faster. And so we normally say the frequency is the velocity divided by the wavelength. But in a situation like this, where the observer is moving into it, we could say it's kind of the equivalent as if the waves were traveling faster by the rate at which the observer is moving. And if the observer was moving away, we'd put a little minus sign. Now then, of course, we could have something that looks like this, and so plus, minus. So plus when it's moving towards the source, minus when it's moving away from the source, and then this is the speed of the observer. Now, if the source itself was moving this way or this way, it would crunch the waves together or spread them out, and so there would be a change in the wavelength. If it was moving towards, and I'll put a little S for source, there'd be a minus and then a plus. And so I guess what we would say, and we like to use like a little F prime to kind of say this is going to be that new perceived frequency. And so it'd be the velocity of the wave, and then the plus sign for an observer that's moving towards the source, or a minus sign for an observer that's moving away. And then here, since the wavelength changed, we could write this as wavelength as a velocity of the wave divided by its frequency. And then we would do the minus if the source is moving towards the observer, or the plus, which would stretch the wavelength out by a little bit if the source was moving away from the observer. And so we always like to kind of put the sign at the top for when they are approaching each other, and then the minus when they are separating. And so we've got, 4 combinations. The observer can be going left or right, or the source can be going left or right. And so in this case, if the observer was going to the right, that would be towards the source, we would use the plus sign. And if the source was going to the left, that'd be towards it, we would use the minus sign. On the other hand, if the observer was moving away, we'd use the minus sign. And if the source was moving away, we would use the plus sign. And so there's those 4 combinations. And so they could be going in the same direction. And so one would be moving towards it, and the other one would be moving away. Anyways, so hopefully you see all 4 combinations. Now, the hardest part of this little mini lecture here is, how much has the wavelength changed? And of course, that's related to how fast the source is moving. And so we would like to say it's V of the source, and then it would be one time frame, one cycle before it made its next wave. In fact, we can write the period then as its reciprocal. So I'll get rid of that and put it over its reciprocal, because this leads us to the main equation, kind of quickly, hopefully not too quickly, but I'll call it a little mini lecture here. But what it means then is if we take the real frequency, the frequency at which this little object is oscillating back and forth, and then multiply it by these factors, and there's three different speeds here that can really get confusing. The v itself is the speed of the wave, and then the VO is the speed of the observer, and the VS is the speed of the source. But once you figure out the individual three speeds, then, of course, also which way they're traveling, the plus or the minus in the top, or the minus and the plus in the bottom, then you would get the perceived frequency shift. Okay, so in other words, all of this is a long way of saying is that there is a frequency shift, more, I should probably call it more of a perceived frequency shift. Now, we call this the Doppler effect, when either the observer, the source, or both are moving, and this is that mathematical relationship. And that's what's happening here. What we have here is a bell that's ringing, and so there's a bell, and it's putting out sound waves. And the sled rider is coming along. Probably, you've seen this Olympic event. They're kind of on the sled, on their back, riding along, and they'll hear this sound. And of course, at first they'll be approaching the bell, and then they'll pass it, and then they'll be going away from the bell. And so there would be a Doppler effect, a perceived shift in the real frequency. I'll call F the real frequency of the bell, that, you know, they would hear then a higher frequency coming towards the bell and then a lower one. But never along this path, since this person's moving, do they ever hear the, I'll call it the true frequency. They always hear a perceived frequency that has been changed because of their motion. So let me call this F prime as the sled rider is coming in. So I'll call this F prime 1. And then when the sled rider or the luge is now exiting, let me call that F prime 2. So F prime 2. And so let's apply this equation from our little mini lecture, starting with this idea that here is the velocity of the observer, and here is the velocity of the source. And the source is not moving at all. The source is just this bell hung on the side of the track, and so that the rider, you know, it's an Olympic rider, so they've learned to judge their speed based upon what frequency they hear. And so that's how they know if they're entering the turn too fast or too slow for what they've planned for their race, you know. And they gotta, you know, to win, that's where the skill comes in, to adjust your speed just at the right time, but always have it fast. And, you know, too fast actually can be a problem, not going into the turn, but usually coming out of the turn, and you crash or you end up in the wrong part of the ice. And so, believe it or not, too fast is an issue for your skill level. So I'm just going to put a V down here because this right here is the source, and the source is 0, okay? Okay, so then I'll put a V and a V here. Okay, there's the waves. Remember the plus and minus, and so we said use the plus sign when you're approaching the source. So in the first case, I'll put a plus sign, and in the second case, I'll put a minus sign because we're now leaving the source. And your observer is going to be moving at some speed V naught. And I'm just going to take it as immediately before and immediately after. So there really is no change in the magnitude of the speed of the observer. Okay. And then, of course, times this F, which is the frequency of the real bell. So if anything in this problem, what can get confusing is just the conceptual understanding. I don't think the math's going to be real hard here, but knowing that there are 3 different frequencies we've got to be talking about and 3 different speeds, we're talking about. And keeping them straight with the pluses and minuses can be a little daunting. To add to it, they don't really actually give us a number for any of these, right? It just says, let's go back here. So when her sled passes the bell, she hears the frequency of the bell fall or lower by what's called a musical interval as a minor third. And I guess we probably don't need to worry about the music side of things. That is, the frequency she hears drops to 5/6 of its original. Okay, so that statement is saying that frequency number 2 is 5/6 of the original value she hears. Okay, so calling F prime 1 what she hears going into the bell, and F prime 2 what she hears going away from the bell, this is 5/6 of that. And that's putting those words into an equation. So then it says, find the speed of sound in air at an ambient temperature. And so it's minus 10 degrees. All right, well, I'm going to need another page here. Let me call this page 1. Okay, so on the page 2, we can say the velocity then is 331 times the square root of the temperature on the Kelvin scale divided by 273. All right, so if I take the Kelvin scale, which would be, let's see, 273 plus the temperature in Celsius, which is negative 10. And so my Kelvin temperature is 263. If I divide that by 273, if I take the square root of that and multiply it by 331, I get about a 324.9 meters per second. Now, by the way, we did a long problem, number 4, in the last video, and did a binary expansion on this square root, and said sometimes it's a lot easier to use this approximation. And so this should give me roughly the same speed, 331.5 plus 0.607 times the temperature of negative 10, and that's a 325.4. So it is close, off a little bit distance, but they each round 325 to be off as expected here. So maybe I'll just use the 325. That's 3 significant figures. I won't worry about that difference. But there's, I think, the part A and probably the easier part. In fact, they kind of were helping you because everything we just said back here on page 1 is we need to know this V. We need to know the speed of these sound waves. And so that's why the temperature is given. And that's this question. Find the speed of the athlete. And so we're trying to find this observer speed, V naught. So why don't I, since I know this ratio, why don't I divide these two equations, one over the other? So this will be F1 prime over F2 prime equals, and maybe for this F1, I'm going to write it as V plus V naught times the real frequency over velocity. Okay, so that's this F1 prime. I'm going to write this one as V minus V naught over F over real speed. And I like that because I noticed that they each had a real frequency and a speed by itself. So when you write it as a ratio, those will go away and cancel. So that's a good, nice first step. And then there's this ratio. is what we have here, although I guess we're going to have to rearrange it and put 6 over 5 for V1 over V2 to make it match what I need over here. So this is a 6 over a 5. And then I get the speed of the wave, which I'll take as 325 plus V naught. And down here, 325 minus V naught. And now I just need to solve for V naught. And so I'll just do the means extreme here. Or should I change that to a decimal? Yeah, I'm going to change that to a decimal. So 5 goes into 6 one time, and then there's a 5 left. So that's 1.2. So then I'll move this over to here. So this will be 325 plus V naught. And then 1.2 times 325 minus V naught. And we distribute this 1.2 times 325. We get 390. And then, of course, I just get 1.2 V naught. And if I move the V naughts together, I'll get 2.2 V naught when I take this one and bring it over. And then over here, I'll get the 390 minus the 325, which leaves me with a 65. And then finally, to get to the answer, I've got the 65 divided by 2.2, which is about 29.5 meters per second. Which, it's hauling buns here. That's 65 miles an hour. So that's fast. That's flying. And I think that's it. Okay, good. And so that's a good example of a Doppler one. And again, it's blue. The math didn't seem to be worthy of the blue marking, but I do think the understanding of the problem, the 3 different frequencies, the ratio of them, and the 3 different speeds, the whole Doppler effect, certainly I would give it a difficulty level of blue. Probably every Doppler problem probably gets a difficulty of blue, depending on what you're doing here. Because I think this one, yeah, I remember this one here. I was reading this. This is a little harder. Still probably blue. Now, it doesn't go up to the way of magenta yet. Maybe, but listen to this one carefully. Here's a bat moving at 5 meters per second and is now chasing a flying insect. If the bat emits a 40 kilohertz chirp and receives back an echo of 4.4 kilohertz, what is the speed of the insect moving away from the bat? And go ahead and take the speed of sound in air to be 340. All right, so remember 345 is room temperature, so we're probably looking at a little bit less than room temperature, maybe that's like maybe 20 degrees Celsius instead of 22 degrees Celsius. In fact, we do a lab coming up where we measure the speed of sound and then use that, work backwards to get the temperature in the room. And then we also do a hot environment and a cold environment and see how it changes, and then use that speed of sound again to get the temperature of those environments. So if that helps the next lab we do, that's how we're going to do it. But anyways, let's talk about this bat here, because this one is really, what does a bat look like? I don't know what a bat looks like. That's a terrible looking bat. But this bat sends out some sound waves, and then it hits this flying moth here. And the moth is going to then, of course, hear that. Now, I don't really know how much I should emphasize in this chasing, because insects aren't real bright, although they know when they're going to get attacked and eaten. So I'm pretty sure the bat is flying towards the insect, and the insect is doing its best to get away from the bat. I do see a higher frequency, which happens when they're moving together, but it also happens just when the bat is flying at a faster speed than the insect and closing it up. So, why not we do this? We'll just kind of start the problem by giving a direction to the bat and leave it open for the bat going either direction. But in my diagram, I'll kind of indicate that it's going this way. And so maybe I'll put I for insect and B for bat. And, maybe if we go through all this math and we come out with a negative number, then the insect is being very dumb and flying towards the bat. But I don't think that's the likely case. So, but at least that'll give me the mathematical ability to solve the problem for either option. And so the freedom of choice is made with the bat flying one direction towards the insect. That's kind of given there. And then this one I'll give kind of the mathematical option, and we'll see what it comes out. So if we get a positive number, then the insect is going away from the bat. Although, again, we're going to find out, though, it'll be less than 5, because it's, the frequency's increased on the echo. So it's got to be, the bat's got to be closing the gap here. Okay. Let's see. Here's what kind of makes this, though, a challenging problem, is if we just calculated the Doppler effect once, this would just tell us what the bat hears. The insect hears from the bat. Because, and maybe I'll grab a different color here, because now there's going to be an echo, at which point you could think of the sound originating off the moth and then being perceived by the bat. And so that too would have motion and then have a secondary effect. It's why I don't really want to call the bat the source or the observer, because the bat is both. The first part of this calculation, I'm going to say the bat is the source and the moth is the observer. Then on reflection, the moth is going to be the source and the bat is going to be the observer. So let me, kind of break my page into two parts here and say, okay, so the first frequency, I'll call it F1 prime, because this is going to be the shift in the frequency as it is then received by the observer, which is the bat. So when we write our general equation, and maybe you remember the little mini lecture we did back here in 36, this would be the V of the waves plus or minus V of the observer, V of the waves minus or plus V of the source times the original frequency. And the original frequency, I'm quite sure that's what they mean here. The bat emits a chirp of 40. Okay. And so in this case, I'll put the V and the V. Those are the speed of the wave. That's given straight up as 340. And I'm going to then look at the pluses and minus. The top is the observer. So in this case, the observer being the insect, I'll say V of the insect. And the insect I've got labeled as a positive number when it is moving away. And so when it moves away, that's what the minus sign is for. And now you can see in the mathematics, if my assumption about the moth is wrong and the moth's going that way, this is going to come out to be a negative number, which is the equivalent of having a positive here with a positive number there, and it's moving towards it. So that's why mathematically this will work out with either way the insect is moving and the positive is moving to the right. And like I said, I'd be kind of surprised, but possible, that the insect is going towards the bat. It's not going to go away from that sound. It's, like I said, I know insects aren't real bright, but they're bright enough to avoid their predators. Okay, now down here is the velocity of the bat. That's our source here, at least in the first Doppler effect. And it's moving towards, which we use the minus sign. Okay? And so we use the lower sign moving away. So observer moving away. And we use the upper side when it's moving towards, and that is the source is moving towards the bat. Okay. Now, if I put in my numbers here, this is 340 minus the velocity of the insect, number I don't know. Here is 340 minus the velocity of the bat, a number I do know, that's given at 5 meters per second. And a frequency, I do know, 40 kilohertz. And then this would be that frequency shift number 1 that the moth is going to hear. So that's what the moth would hear. And of course, I don't know the speed of the insect. So at this point, I can't calculate what the insect is going to hear, but I think we're going to get that when we set up the second equation. So then we'll have 2 unknowns and 2 equations here. Okay, now, just to change colors and go to the second one. So the echo comes over here. So let me call that frequency number 2 prime. And that would be the velocity of the wave plus or minus the velocity of the observer divided by velocity of the wave minus or plus the velocity of the source times the frequency that it comes from. And let me start right there, because the frequency coming off the moth is this number, F1 prime. And I think that's the key to the problem, is to realize that there is 2 shifting of frequencies. So there is first the source here, then the echo. The source is from the moth getting back to the bat. And so this then is the frequency that gets observed at the bat. And so this is the 40.4 kilohertz. And the speed of the wave doesn't change, so put both 340s here. And in this case, now the observer, right here, is the bat. So that's a 5. And the bat is coming towards the source. So that'll be a plus. And then down here, the source is the insect. And the insect is moving away, and we use the lower sign for away, from the observer. Unless, of course, like we said, we can get to a negative there. Okay? And then this is that F1 prime, which what I'm going to do is take it from here and put it over to here. So let's put these 2 equations together here. And what we get is this 40.4. And let me just drop the kilohertz. Here, let me just put that as 345 over 340 plus the speed of the insect. and then times the frequency that, got to the bat, which is this calculation. And so this would be 340 minus the speed of the insect. And downstairs, 340 minus 5 is 335. And then, of course, we've got the 40. So if we simplify things a little bit, 340 minus initial speed, not initial, insect speed, and 340 plus insect speed. And we grab a calculator here. I can go 40.4 and divide by the 40. So that's moving the 40 over to there. I can also divide that by this number, 345. And then I can also multiply it by 335. And so that all comes out to be 0.9807. Well, what if I should take 4 significant figures? But I will there. All right. So now, again, just a little bit of mathematics to solve this. Let me move this over to here. So this is going to be the 340 minus the insect speed. And then this is going to be that number times 340. So it's going to be 333.4 plus, move this over, 0.9807 VI. If I bring this negative over to here, it becomes a 1.9807 V of insect. And then this is this 340 minus the last answer. And so we're looking at about a 6.554. All right, and then I'll divide that by 1.9807. And that should give me an insect speed of about and I'll now just do 3 significant figures, 3.31 meters per second. And again, it kind of fits what we were talking about at the beginning. It's a positive number, and it is less than 5 for the bat. So the bat is closing the gap. That's why the frequency shifts upward on echo. But the insect is moving away, is a positive number. Good. And hopefully that one wasn't too bad. All right. And one more here. Looks like a Mach speed one here. Here we got a meteor about the size of a truck enters the Earth's atmosphere at a speed of 20 kilometers per second, and it's not significantly slowed before it enters the ocean. All right. So we got this thing moving at an incredibly high speed. What is the Mach angle of the shock wave from the meteorite in the atmosphere? And go ahead and use 331 for the speed of sound. Assume that the meteor survives the impact with the ocean surface. Yeah, right. What is its Mach angle? Okay, so maybe we should talk about Mach speed, Mach angle, because if you're going faster than the speed of the wave, and it's probably easiest to see with water waves because many boats, go faster than water waves. Water waves are pretty slow, these surface water waves. And, well, if you're in the harbor, you will go slow. But out on the ocean or out on the lake, you're going to go faster than them. And what happens is you get a wake. This is a superpositioning of all the waves. So we call it a wake when they have to do with water waves, but when they're sound waves, we just call it a shock wave. But in either case, you can kind of see some easy geometry here. If the sound is produced here, and then a time later, the object, which in this case would be the meteorite, has traveled to here, then this distance, d, is the velocity of your object, and sometime later. Now, the sound goes out and really only travels this distance, a shorter distance in that same amount of time. And that's why each location where the object makes a sound, this builds up a wall, a superpositioning. And so that's what it is. Instead of having individual waves and hearing a different frequency, you actually hear all the waves clumped together and you have just one big thud, boom, boom, or if it's one big wave, if it's a boat going through the water, it's a wake. So this distance here, d, maybe we should call that d1 and this d2, would be the velocity of the wave times time. I'll just use v for my, wave. In fact, it's running through my mind right now. Let me just grab the book here. What symbol the author uses. Oh, that makes sense. He uses v for the velocity of the wave, good, and then he uses an s because that's the source. Okay, so I should have not used a not for the object. I should have used the source making the waves. Yeah. But the point is, we have a little triangle here, and then we have some angle here, theta. That right there, that angle between the movement of the object and the wave itself, the shock wave or the bow wave, if it's a boat, is then what we call that Mach angle. And so we got a nice little right triangle here. And so if we go sine theta, we would get this distance, d2, over the hypotenuse, which is d1, which we can write as velocity of the source t divided by the velocity of, divided by the source t. And the times cancel off. And so you just get the velocity of the wave over the velocity of the source. And so if you know these two, or this ratio, you can get the Mach angle. And that's what they're asking in this problem. What is the Mach angle? Now, let's talk about the Mach. Mach, then, Mach, is how fast is your source compared to the speed of the wave. So a Mach 1 means you're going the speed of your source, which, if they're sound waves, that would be the speed of sound. And then Mach 2 means your source is going twice the speed of sound. And Mach 3 would be 3 times, and so forth, and so on. Okay? So, in our case, our Mach number, which is, I'll write as 20,000 meters per second. Now, was given in the problem here, 20 kilometers per second. And the speed of sound, 331 meters per second, gives us a huge Mach number, 20, 1, 2, 3, divided by 331. And so this is over 60 times the speed of sound. So my Mach number is, 60.4. And you can see that the reciprocal of the Mach number is this. And so sine theta is 1 over your Mach number. So in this case, 1 over 60. And so for big numbers like this, you can see that the meteor is going to move really far compared to this distance. And so you're going to have a very narrow or small angle. Again, like a boat going through the water really, really fast, the wake will be really narrow. And then you slow the boat down, you can spread out the wake. In fact, kind of a fun problem I worked on years ago in Boeing, we were calibrating the satellites, and we put up some satellites, and we could look down on the Russian fleet and pick out their speeds. Their speed was very easy by processing the wake, and so we just had a little algorithm, took a picture. The wake stands out like crazy, the white water, the wake in on the blue or green water, and so it's pretty easy to get that angle and then figure out the speed of the boat or ship. Okay, but back to this problem. Let's see. Let me change my calculator to degrees. And so let me go inverse sine of 1 divided by 60.4. And, 1 degree? Whoa. Okay. 0.95 degrees. I feel like I hit something wrong here, but that's it. And I did say it's going really fast. It, goes 60 times this compared to that. So we've got, if I draw that 6 centimeters, 6 centimeters-ish. 1 centimeter. Oh, 60. I did 6 to 1. Yeah, 60 to 1. Oh, crap. All right. So, I'll say there's my angle in the air. So what is the Mach angle of the shock wave of the meteor in the atmosphere? Assuming the meteor arrived and impact on the surface, what is the initial Mach angle? So kind of the same idea then in B. We need to get a Mach number. That's going to be a little lower number because we've got the source divided by the speed of the wave. And the source, I think they implied it doesn't change its speed or initial. It says, assuming the meteor arrived and the impact of the ocean, what is the initial? So I think they still want us to say it's traveling at 20,000 meters per second. And now we would need the speed of sound in water. And they even show us the table and say, okay, go to your chapter 17. So let me grab the book again here. Chapter 17. And right at the beginning here. Oh, this is the end of 17. So here's this table. Here's liquids. Here is seawater. So 1,533. Okay. So 1,533 meters per second. So my Mach number, 20,000, 1,533, is only 13. So my Mach angle, so sine of theta, is 1 over 13, or theta is the inverse sine of 1 divided by 13, which is about 4.4, still pretty small angle, degrees. But, yeah, about 4.5 times bigger. That kind of makes sense. That's about, well, these aren't linear functions, sine, but they were linear functions, and we're at a small angle, so they're approximately linear. Now, the speed of sound is about 4.5, 5 times that of the, well, it looks like, yeah, 4.5 to 5 times the speed in the air. So makes sense that the angle would be about 4.5 to 5 times more. All right. Oh, perfect. So we're done with those 3. Hopefully that helped somebody. Take care, everybody.